Okay, so today what we are going to talk about is basically the indexing and scaling strategy in MongoDB. So far, what we covered is a kind of basic concept of and basic utilization of MongoDB. So we talked about NoSQL concept, how it's different from relational database design. And we talked about how to do data modeling in MongoDB. So again, there are two different documented structure we can utilize. The first one is embedding, and second one is referencing. So if you use referencing, it's similar to the relational database system. If you use embedding, basically you are embedding those parts which you need to access together fast and just put it in the main document. So depending on which design you use, the speed of operation will change a lot. And also we talked about CRUD operation, create, read, update, delete operation in MongoDB. So we can use the querying and updating and aggregation in MongoDB using different functions. So again, the query in MongoDB is more like a programming language. So far, based on everything we covered, actually you will not have any problem utilizing MongoDB. So using all this knowledge, you can actually install MongoDB server, and you can make and kind of set up MongoDB server on your organization or company, and you should not have any problem of utilizing it. So that's there. However, if you want to increase and if you want to achieve extra performance, there are some advanced concepts you can utilize too. So advanced concept, something like this, import and export database. So about that, I already uploaded the MongoDB database tools, how to set up it on the Blackboard. So you already did it. And for the assignment 4, you already tried the import and export the database. So I'll not cover this part. And there are two strategies to help you improve performance much further. The first one is the indexing strategy, which also exists in the relational database system like MySQL. And there's also scaling strategy. So I'll talk about this more today. So first of all, the indexing strategy is this. So for indexing, for the concept of indexing, you can think of something like this. Let's say that there's this dictionary, and you want to find a certain word. Then there are two possible ways, right? The first way is that you can scan from the first page to the last page to find the word you want to find. Then the problem is that it'll take a very long time. So you have to have a faster way to find your word and more efficiently. So if you look at the dictionary, actually they have something like this on the side of the book. And it says A, B, C, D, E to the Z. So you can, if you want to find a certain word, you can look at the first character of your word and you can find from there. So basically it will help you scan the book much faster. So basically indexing is the same. Basically it helps you scanning the page much faster by utilizing index. So this is the concept of indexing basically. And in MongoDB and relational database system, you can utilize this kind of indexing concept. So if I talk about indexing in MongoDB more, basically it's there because it supports the efficient execution of query. So without index, MongoDB will perform collection scan, which is basically same as the table scan in the relational database. So if you didn't make any index on your collection, the MongoDB will scan every document from the first document to the last document in the collection. So it will be quite slow to scan entire documents. However, if you set up appropriate index in the MongoDB collection, the MongoDB will scan a certain part of a collection based on the index you made. So it can increase the speed of operation in the MongoDB by limiting the number of documents to be scanned. So that's the basic concept of index in the MongoDB. And when you make index in MongoDB, it uses special data structure. So basically, the index is created and it will store a small proportion of a collections data set in an easy to scan form. So I'll talk more about this later. And basically, what they store in the index is this: the value of a specified field as an index by you, and the index will be sorted by the value. So it can provide efficient matching in query operation, basically. And here is how the index will work in the MongoDB, basically. So here, let's look at this, the figure. So the second part here is the data page. Basically, each data here is a document. So you can consider each green D as a document in a collection. So you have a huge number of a collection. Let's say that this is a user collection. Then each document represents a user information. So there is a user stored like this. And it is possible that a user, when they use your application, they may search a certain user based on their age or not. Then you want to perform that query operation to happen as fast as possible. Then what you can do is that you can create an index based on the age of a user. So let's say that then you can create the index based on age of a user. Then for this document, the user's age is 4, and this user, the age is 7, something like this. For this user, age is 10, this user age is 16, something like that. Then basically, the index will keep two things in MongoDB. So if you make an index based on the age of your document collection, then index will keep the index the field, which is age in this case, and it will also keep data location on the disk. So for this age 4, the link to the document is this age 7, link to the document is this is age 8, link to the document is something, this link to the document is something like this. And this age will be stored by sorted. So from the smallest stage to the largest stage like this. So if the index is stored like this, basically we can search document much faster. So let me give you an example how fast the MongoDB can scan a document when there is an index. So let's say that how many documents the MongoDB need to scan to find all documents with the score 16. So yeah, earlier I said age, but let's say they just score. And if we want to find the documents with the score 16, then if we don't have an index, basically, if we don't have this index and if the document is not sorted, we have to scan the entire collection to find all the documents with the score 16. So if we assume that there are n documents in a collection, the total number of scans we need to take is n if there's no index, because we have to check all the documents to find score 16 documents. However, if we have an index like this, so there is a score value retrieved from each document, and they are sorted like this, then to find score 16, we can simply scan this. It's smaller than 16, smaller than 16. We keep scanning, and we found here this document. This score is the same as 16. So we go to the link, and there's a document. We retrieve that. And next document is also 16. We go to the document and we retrieve that. And next one is bigger than 16, and then we can stop here. We don't need to scan anymore. So in this case, the number of documents we need to scan is 22, basically. So in this example, we have to scan 22 documents, and on average, the total scan will be less than n. So we don't need to scan entire document in the collection. We can keep scanning until we get the results we want, basically. But this is when the indexing is done in a naive way. Actually, in a MongoDB and any other like database application, when you use indexing, usually they are sorted based on the bit tree structure. So you don't need to know exactly how the bit tree structure works, because it's more of a data structure and algorithm part in the computer science. But let me give you like a simple information why bit tree structure is much faster. So it's the same example as earlier. So if you basically, if you make index using the B-tree data structure, like MongoDB and any other database system, then the index will be sorted in this way and stored in this way. So basically, what happens is this. So if we want to find a document with the score 16, it goes here first, and you look at the first number, it's 40, it's bigger than 40, so it goes to the left here. The first one, score is 10, it's smaller than 16, so we go to the next one, it's bigger than 16, so we go to the middle link. Middle link is here. And here, 10 is smaller than 16, so we go to the next one. And this is 16, so we find the link and we retrieve this document. The next one again is 16, we find the link and we retrieve the document. And next one, there's no more, so we stop here. So if in the same example, if the indexing is done with the B-tree structure, basically how many documents we need to scan is here: 1, 2, 3, 4, 5, 6, 7, something like this. So in this case, I wrote down 6, but actually 7. The total scan the MongoDB will be 7. So on average, the computer scientists, they calculated this number. Basically, on average, when index is done with the B-tree structure, they can scan only log n number of documents in a collection to get the results what they want. So index, if you basically, the thing is this, what you need to know is that if you use index appropriately, it can increase the performance of a query much faster. So if you want to find a certain document given a certain field, and if that field is indexed, basically the query performance will be much faster. That's the most important thing. So how the indexing in MongoDB works. So let's look at this example here, basically. So in MongoDB, basically, to summarize, it will be indexed with a B-tree, and this is similar to the indexing in relational database. So when we talk about the MySQL, I didn't really talk about the indexing part because of the time limitation. So if I give you a brief information here, in relational database similar to MySQL, when you create a table with the primary key and foreign key, you don't need to make an index by yourself, actually. In most of the, these days, in most of the relational database system, they create index based on what you set as a primary key and foreign key automatically. So if you go to the relational database and if you look at the older system database, which we created last time, then you will see that inside the customer table, if there is we usually looked at the column information, but if you open index part, the primary key and the foreign key is already indexed like this. So you can see that it's indexed like this, and there are more information about how it is indexed. So again, even in relational database, the primary key and the foreign key is indexed based on B-tree data structure. So that's how the relational database is doing. And that's why relational database can be performed fast, because they are already indexed based on primary key and the foreign key. And when you join, they are utilizing this index information. In the MongoDB, it's similar. So it can improve the performance significantly if you utilize index well. And how to make an index in MongoDB is basically this. But the problem is that in MongoDB, you actually have to create your own index, because again, in the MongoDB, there is no concept of primary key and foreign key. So basically, from the system perspective, they don't know what will be primary key and what will be foreign key. So, and they don't know which kind of a field you are going to utilize to retrieve information. So that's why in MongoDB, you have to create index by yourself. And making an index is quite simple in MongoDB. You can simply use the database dot the name of a collection which you want to add index, and you can use the create index function. And here you can specify the field you want to make an index, and you can specify number 1 or -1. If you specify 1, basically the index will be sorted in an ascending order. If you specify -1, index will be sorted in a descending order. So that's the only difference. So let's try this. Let's try this a simple example. So let me turn on the Robo3T and let me connect to the local database. So if I go to the test database and go to the collection, so last time we are going to utilize restaurants. No, so I don't have it here. Yeah, I think it's because I didn't import to restaurant database here, but they will take a little bit of time. So yeah, let me skip this. You can try it by yourself because you already did the assignment 4. So you have a restaurant collection inside your inside your MongoDB. So let me skip this here doing it, but let me show you the example here on the slide. So basically, if you don't make an index and if you just perform this query, basically this query is this db.restaurant collection.aggregate function. And what I want to do is that I want to sort all the documents in the restaurant collection based on the borrow. So if I perform this query, then basically total time it takes is 0.153 seconds. However, if I make an index first, so if I make an index on the restaurant collection based on the borrow, then basically this index will keep the borrow information, which is retrieved from all the documents in the restaurant collection, and it will be sorted in an ascending order. So it's already sorted index based on the borrow. So later, if we design aggregate query, and if we use a sort operator based on the borrow, then it will take only 0.013 seconds. So it will be more than 10 times faster actually, because we already have this index sorted. So we already have a document sorted based on borrow. So in this case, we don't need to sort again because we have already sorted documents. So when you perform this query, MongoDB will simply look at the index and retrieve documents to you. So it's much faster. So that's how you can utilize your index. And let's look at more like the advanced concept of the index. So when you design an index in MongoDB, you can design a single index or compound index. So single index is basically indexing on a single field. So something like this. If you want to sort this document based on the score, you can only retrieve a score and you can put 1 to sort it in an ascending order like this. And compound index is indexing on multiple fields. So in here, you can specify a hierarchy on sorting order. So you can say that you want to sort the document based on the user ID first, and for each user ID group, you want to sort it based on score. Then you can specify something like this. So when you design an index, if you design something like this, what it means is that you want to sort all the documents based on user ID first, based on ascending order. And for the documents which have the same user ID, for those documents, you want to sort again based on the score information in a descending order, something like that. So basically, if you look at here, there's AA1. So from here to here, it's all documents with the user ID AA1. And you score based on you sort based on the score. So from here to here, it will be sorted in a descending order. So something like this here. So if there's 3 CA2 documents inside your collection, it will be here because CA2 is bigger than AA1, smaller than N. So it's here in the middle. And these have the same user ID, but the score is different. But then they are sorted again based on the score like this. So that's the compound index. So it's making hierarchy. It sorts first based on user ID, and for same user ID group, it sorts again based on score. So how to make a compound index? Basically, it's the same. You specify the db, the collection name, and you create index function. You specify the first field you want to sort. You specify the second field you want to sort, and you can add more hierarchy if you want. So for the restaurant collection, if you want to sort it based on the borrow and cuisine, you can specify borrow 1. And in the same, for those restaurants in the same borrow, you can sort again based on cuisine. So this one is an example of a without compound index. So if you don't make a compound index, and if you perform this kind of aggregation query, which is search based on borrow and QGIS, it will take a much longer time than the same query with compound index. If you use compound index first, and then if you run the query, it will be performed much faster. Same here. So in this case, we use the aggregation function and we use match first based on the borrow. So so we want to only use a restaurant in the Brooklyn area, and our compound index, we sort documents based on the borrow first. So this will utilize this index. So the speed will be much faster if you use index in this case. If you don't use index, it will be much slower like this. So that's some example of speed comparison. And there is something you have to think about it. So when you create index, so when you design an index page, let me look at one question here. Will we benefit when we do query on score? Oh yeah, so actually this is what I'm going to tell now, but yeah, this is a very important question. So yeah, so let me talk based on this example here. So let's just say that we made an index like this. On the restaurant, we use the create index and we made a compound index, borrow, QGIS. So it will be sorted based on borrow first and then QGIS later for the same borrow group. So in this case, if you run a query like this, borrow Brooklyn and QGIS America. So if you, in your query, borrow is used first, then in your index, borrow is used first. So in match, right? So you will have a speed gain. So speed will be faster. And also borrow is first level, QGIS is second level. So here same, borrow is first level, QGIS is the second level. Then it match with this index. So first level, second level, first level, second level. So it match. In that case, the speed gain is there. So your query will be performed fast actually. But I think it's in the next page. If you use the QGIS first, then you will not gain any speed actually. The performance will be same as not using index because the level does not match. So when you design an index, there is a first level, second level. In your query, it should be the same. The first level should be matched and first and second level should be matched. Only in that case, you have a speed gain. And how to, and there's actually no, if you are not sure whether your query will utilize index or not, there is a way to check it. So let's say that this is the query you want to try. So on the restaurant collection, you want to find all the restaurants in the Brooklyn borough and QGIS American. Then you will design this query, but you are not sure whether this query will utilize this index you created. Then you can type your query, and at the end, you can type that explain function. So if you do this in the MongoDB, it will give you this kind of result. Basically, it will explain about your query, how your query will be performed in MongoDB. So there is a query planner. So if you open it, there should be winning plan. If you open it, there is an input stage. So if you open input stage, there is a stage here. In the stage field, it will say IXScan. And there's an index name. Index name, it will say borrow QGIS. It means that the index scan will be performed based on your query, which means that your query will utilize index, so the speed of operation will be fast. So that's how you can check. Let's say that so again, if you only use borrow Brooklyn, basically the first level match. So first level here is borrow, and in index first level was borrow. So in this case, if you use explain function, again, it will show the same results. So stage is IXScan, index name is this. So this index will be used for your query. So basically, index scan will be performed. So you have a performance boost. So basically, this is the key point. As long as the query follows a hierarchy in the index scan will be used and you will gain the performance boost. So that's important. However, you may design a query something like this. So earlier, when we design index, we used to borrow first and QGIN as a second level. But in your query, if QGIN is the first level, it doesn't match with your index you created. And also in this case, QGIN is first level, borrow is a second level. Again, this doesn't match with the index you created. So in this case, if you use the explain function to see how your query will be performed, then it will show slightly different information here on the stage field. On the stage field, it is a collection scan. Also here, in the stage field, it is a collection scan. It means that collection scan will be performed and index will not be used on your query. In that case, you can assume that the MongoDB will scan entire document in the collection, so the speed will be slower, basically. So that's how you can check whether, basically that's how you can utilize index, and also that's how you can check whether your query will be utilizing or not the index. So that's so basically that was the most important part of the indexing, and MongoDB actually provide a more powerful index function. So I want to cover this a little bit here. So there's a geolocation index. So let's say that your data set, like in your document, you have information, something like a GPS information, or you have a longitude information and latitude information. Then you can actually utilize this geolocation information to make indexing. Basically, you can create geolocation index based on this kind of information. So if you make a geolocation index, later when you do query in MongoDB, you can try more powerful query. You can use a distance query. Basically, let's just say that in your data set there's a restaurant, and you want to find any other restaurant within 10 miles of a certain restaurant. You can design a query, something like that, based on the geolocation. So I will not cover too much about that here in this class, but the information is here, so you can go there, then you can check it. And this is a quite powerful function. And also there is something called text index, which you can create. This is also powerful because once you, let's say that you have a field in your MongoDB document, and that field will contain text information. Then based on textual information, let's say that you want to do some natural language processing later. Then you can create text index on that field. And if you do that, it will support the efficient searching for string content in a collection. So let's say that the text field contain like a long description or like long text written by a user. And if you make a text index, it will only store root words, which means that it will ignore stop words, something like the, a, or, and also it will stem the word. So if the word contains like playful, playing, plays, it will be all considered as the same word as play. So if you are familiar with the natural language processing, you may understand the powerful feature of this kind of like stemming or ignoring stop words. But this is not the natural language processing course. I will not talk too much details about it, but this is a really powerful feature. So if you use a text index later, when you try to do like a text searching, it can be really powerful, and it can save a lot of time for you in terms of natural language processing. So more information is here, so you can check it. And I put some simple demo here actually based on the text index, because it's quite useful function. So you can try this later based on your restaurant collection. So to make a text index, basically you can do this. You can specify db, that name of the collection, and create index function. And you can specify the text field which you want to make an index. And earlier, when you put the field here, you put 1 or 0 here based on this ascending, descending order. But in this case, this is a text indexing. So to create text index, you can specify text field here, which you want to make an index. And you can specify text with a double quote like this. Then this field will become a text index field. And let's say that your document contains a lot of text fields. And for all the text fields, so for example, here we have a street, which is a text field. We have borough, which is a text field. We have a cuisine, which is a text field. We have a name, which is also a text field. So for all these textual fields, we want to make index for everything. Then you can also use this formula. You can use a dollar star star with a quotation, and you can specify text with a quotation like this. Then for all the fields in the document, the text index will be created. So if you do this, and later, let's say that you want to find the restaurant contains word Flatbush, like here on the street name, there's a Flatbush Avenue, something like this. Then you can use this kind of query, text query basically. So use the find function, and because it's text query, you specify text operator, and you specify search operator, and you want to search Flatbush like this. So this is very powerful. So basically, MongoDB provides very powerful search functionality based on natural language processing. So this will be very helpful information if you try to design a certain application in the future in the practice. So actually, this can save a lot of your time because the natural language processing will be done by MongoDB. So you don't need to worry too much about it. So actually, that's all about the indexing in MongoDB. Do you have any questions before I talk more about the design issue so far about the indexing or anything? Because it's a online session, so I'm a little bit afraid whether there might be anything unclear or something might be too fast or something you might be missing. So if there's anything, please let me know using the chat box. I'll go over there and I'll cover it again. And also later, you can try all the demos here so that you can actually see how it works in your MongoDB. So how other type of file like pictures, audio, and video can be handled? It is a good question. But as far as I know, yeah, I have to search more. The MongoDB will provide an index, something like a text index or geolocation index based on audio or video file. So I'm not sure about that actually. Let me actually check about that and let me give you more information next week. Yeah. So actually, I'm also curious about that. Yeah, but I'm not sure about it yet. Yeah. Okay. Any other questions? Okay, I think that was a good question actually. Okay, so if you have any other question, you can always let me know using the email or Telegram later. If you come up with any other question or something curious, any limitation of number of, oh, actually that's a good question. Yeah, so that's just something I'm gonna talk about it right now. So the answer is no. There's no limit of the, so basically for the number of index you can create, there's no limit by default. So you can create any number of index, but there's a problem. So this is the design issue actually. So I said this, the general rule is that if you make index, it improves performance. So index is a good thing. So you have to make it if you want to increase the performance. But the problem is that some people may misuse index. And if you do misuse of index, it will actually slow down performance. So it's something like this. So something is good, but if you have too much of that, it's actually not good. Something like that. You can think in that way. So some people may do something like this. So if we make index, it will increase the query performance. So what if we make index for every field? So for restaurant document, for collection, we can make index based on borough. We can make an index based on cuisine. We make an index based on name. We make an index based on restaurant ID. We make an index based on address of the building like this. So some people may think that if we make an index for every field in the document, it will be really good. So actually, in practice, it's quite surprised but there are people who actually do that. So this is actually the screenshot I captured from one of the Q&A websites on the and I don't exactly remember where, but on the some kind of Q&A website. So it's a kind of a website many like developers and many like computer scientists or those people like IT people, they ask questions about like coding or other different system like that, and people usually answer there. It's something like a Quora or Stack Overflow, and there one person shared his story. So this person was working as a big data consultant, and basically what his job is like going to different companies, and he kind of help digital transformation of the company. And there was one company he consulted, and he said he shared this story, which is quite interesting. He said that recently he helped a customer optimize his database, and the problem was that there was a write rock on the database. It was running consistently at 95%. So CPU was spiking consistently. So basically CPU was utilizing all the time and making for a poor experience. So the thing is this, if your CPU is utilized all the time on the server, then of course the speed will be slower. So he was examining like many different things in the database system to find out the issues. And when he looked at the index, he found that the customer had too many index. So the company created a lot of index, and he counted there was 126 index created in one database system. And he said that 24 indexes were created on one collection. And because of that, for each, I talk more about this, but actually because of that, for each insert update that modifies the key, MongoDB was having to insert the document and update the 24 index. And this was the cause of excessive write run. So basically, what's happening is this. If you have an index, it will increase query performance. So again, in the beginning, when I talk about the index, I said that index will store these two things. So here is the original document. And when you create index, what's happening is that from your original document, a field that you use for index will be extracted, and data location for the original document will be stored here. So basically, here is a collection of documents, and index will be created on top of that collection. And this should be sorted to provide a faster performance of the query. So here is the tricky part. When you read a document through index, it's fast. But when you update the document, when you insert the document, it will be slow actually. Why is because of this? Let's say that you add a new document with a score 12. Then what's happening is that you have a new document here with a score 12, and the MongoDB needs to find a place in this index. So the MongoDB will examine this index, and it will try to add a 12 between here and here. So MongoDB has to restructure this sorting order. So basically, whenever you add a new document, insert operation, and whenever you change a certain field in the document, let's say that for this document, you may change the score from 10 to like 20, then this sort should be done again, right? So whenever there's an update operation, whenever there's an insert operation into the collection, this index should be reconfigured. So that will take time. So the key is this. So again, going back to this design issue, index increase query performance. Basically, when you read or sort, it increases the performance. However, when you try to insert or modify a document, the cost increase. It will get more slower. And in this case, the customer had 24 index in one collection. So in this collection, you add one document, 24 index should be updated. So it will be very slow write operation. So basically for every new document in a collection, all the index need to be updated. So that's what's happening here basically. if you create too many index in one collection, it will be actually slower because whenever there is an update, whenever there is a write operation, a lot of indexes should be updated at the same time. So that's one of the trade-offs. If you use index, it will increase the query performance, like a read and sort operation. But if you expect a lot of write operation to happen on your collection, then index is actually slowing down the performance of your system. So there is a trade-off. So that's just something you have to think about when you utilize indexing strategy. On the array element inside the field, or index on field containing values in array. Yeah, I think it's possible. I think it's possible, but it might be a little bit tricky because array itself is like a big data type actually, because basically array is a list of elements, because in our MongoDB, one of the data type we can have is a list. So if you make an index based on list field, I think by theory it's possible. Now let's just say that there is one list containing 1, 2, 3, and there is another list containing 4, 5, 6. Then MongoDB will think the first list containing 1, 2, 3 to be the smaller number because the first element is smaller. That's what I think, but I didn't test it. So probably you can test, or yeah, I can search more information. So by definition, I think it's possible, but whether it's efficient or not, I'm not sure, because then index should contain that entire list data in the index. So index size will be big. So I'm not sure whether this could be efficient design. Maybe not. But by theory, I think it could be possible. Maybe, yeah, I think I need to check more about this. Okay, that was a good question. Okay, so that's the main design issue. Yeah, you have to think about when you do indexing. Is there any question? Are there any question about the index? Okay. Okay, so if there's no question, let me go to the next slide. So basically, yeah, so this is the, so after this slide, we'll take a break. So this is the last slide about the indexing. So another design issue of indexing is this. So basically, based on what we talked so far, when you use indexing strategy, you have to understand the query which will be used. So basically, you have to understand the application. In your application, what kind of query will be used most frequently? So if people will search your collection based on like age or user ID or not, then basically you have to then definitely you have to make an index based on age or user ID. So you have to have that understanding. Also, you have to know whether there will be a lot of write operation or there will be more read operation. In general, in many of the web applications, we get a lot of a read operation from the user and much smaller write operation. But depending on your application, it might be different. So you have to think about that. So basically, if there are a lot of read operation, you have to think about what people will use a lot for matching operator. And based on that field, you have to create an index. So that's the important thing. And also you have to limit the number of index in a collection. So you can create as many index as you want by definition. However, if you do that, it will slow down your process because a lot of index should be updated at the same time whenever there is a write operation. And also the last important part is that it is good to ensure that your index will fit in a length. So earlier, yeah, it's related to the previous question here. So one student asked the question about whether it's possible to index based on the array element, basically, whether it's possible to index based on the list field. And I said that it might not be a good design because the list size can be big. This is related to this last issue. Basically, what's happening is this. When you have a collection, basically this working set will be part of your collection. So you have a collection with a lot of documents. And in MongoDB, if your RAM size is big enough, so RAM is basically the computer memory, and then if your collection size is smaller than RAM, then entire collection will be loaded into RAM and the MongoDB will process. Basically, the computer will process the query. And if you create an index, as I mentioned earlier, index will contain a field retrieved from the collection, basically. And it will keep that information with a link to the original document. So index will be added in front of the collection like this. So when the size of index and collection are small enough, they will be loaded together into the RAM. But usually in the big data system, the collection size is very big. So the collection cannot be entirely loaded into RAM, and only the index will be loaded into RAM in most of the cases. But the problem is that if the index size is too big, so for example, if we do make an index based on list, and then index size is too big, then the size of index will exceed the RAM size. Then some part of index will be loaded here, and the other part will be left out in the hard disk drive or somewhere else. Then it will actually slow down the process. So something like this happens. So as your data set grows, the index size also grows because each index contains retrieved information from the document. And something like this may happen. And if index is too big, and if the big data and index is too big, the index size will exceed the RAM size. Then basically, it will slow down the process.